I'm from the University of Sydney from a group within there called the Australian Centre for Field Robotics. And I just wanted to give a little bit of background about that centre. So overall, we're interested in developing the science behind autonomous field robotic systems and intelligent systems, and also in being very involved with industry and uptaking that technology. We've been doing this for a bit over 15 years, and we've collaborated with a large sort of variety of different local groups and industry and government, and also overseas. So as a centre, we're about 130 people, including researchers and also professional engineers. So some of the sort of examples of collaboration, like we span various different industry sectors, including defence, mining, agriculture, of course, logistics, aerospace, and so on. So quite a broad range of different things. When we talk about robots, here's some examples of the systems that we've developed over the years. A lot of people think of robots as humanoid type systems, like Arnie, Schwarzenegger, that sort of thing. But for us, they really come in all sorts of different shapes and sizes, from very small UAVs, flying vehicles, all the way up to 3-story tall, many ton straddle carriers to carry shipping containers around and that sort of thing. And so generally speaking, for us, it's more about how do we get the right sensors into the right place at the right time to get the kind of information that's necessary. And in the case of systems that are actively doing things, how do we get the actuation component in there as well? So many different sorts of shapes and sizes of robots. When we sort of think about what kind of value these types of systems can have to industry, and this is talking broadly at the moment, but I'll relate it to agriculture on the next slide, there's a couple of different ways that this can produce value for industry. The first point is kind of the more simple one, which is simply replacing existing functions that are already there within an industrial process with autonomous versions. And you get lots of benefits like precision, repeatability, and sometimes labour savings as well. But the kind of ones that tend to be more interesting for us are when you start to consider the whole process optimization. So when you look at an industrial process, there are always points of uncertainty within that process, and oftentimes these types of new technical kind of systems can reduce that uncertainty in a way that lets you make the process a bit more efficient. In terms of precision agriculture, when you couple it with sensing, with robotics and so on, you can really have this amazing attention to detail where you're looking at every single leaf, and you saw some really great slides of that in the previous talk. But you can do that across the whole farm, right? You have this very fine detail but very broad scale information. So there's a lot of opportunity to get new kind of sources of information about what's going on there. So just as an example in the kind of agriculture context, and I don't expect you to read all these, and it's probably not quite complete anyway, but if you look at, for example, the process of growing apples, you've got this kind of natural process that happens here from the buds all the way through to the fully grown product. And then you've got this industrial process that sits on top of that. Throughout that process, there are key points where you go into the field and you make measurements, and based on that sort of knowledge and understanding of what you're measuring and what you're seeing in the field, you make decisions about things like, how much spray thinning to do or something like that. You've got these feedback loops about sensing and making decisions. And so we like to look at these kind of diagrams and see, okay, well, where are there key points of where currently there's quite a bit of uncertainty in terms of the quality or the nature of the information, where if we had better information, maybe we could do things more accurately and so on. And, it's sort of like mapping precision agriculture in this thing. And so that brings me to intelligent sensing systems. And actually, this is really the only photo of an aerial vehicle that I've got. I'm actually going to talk about more about the ground vehicle in this talk and show you some of the things that we can do with that on-the-ground sensing. But as I mentioned earlier, in a sense, it kind of doesn't matter. It's about, where does the camera need to be to get the data that you need? And in some cases, it's a satellite, some cases it's a drone, sometimes it's a vehicle on the ground. So this is the autonomous sensing platform that we've been using in our research in tree crops. It's called Shrimp. It's an all-electric powered skid-steered vehicle. It was actually not designed for agriculture specifically. It was designed as a general-purpose research platform for looking at perception and how robotic systems can kind of perceive their environment. But it's turned out that it's been, though we've used it in defence and mining as well as agriculture, very broad sort of use as a research tool, it's been quite appropriate on the orchard. Now, if you're looking at this and thinking, there's no way that thing would drive over my property, you may well be right, but something I like to emphasise is that, don't look too much at exactly the platform, think about the kind of components of technology, and these can be redeployed in any way, shape or form. So when we look to commercialise something, we take a subset of those sensors that we've proven with a research system are kind of relevant, and then build that into something that's a bit more appropriate in a commercial setting. So it might just be one or two of those cameras stuck on the back of your existing tractor or something like that. So we have a large variety of different sensors on here, different cameras, thermal cameras, different kinds of laser sensors, GPS type technology, and also some soil sensing has been added to this platform. The platform can drive itself fully autonomously up and down the rows of orchards like this. An interesting point here is that we actually don't use GPS at all for this. We use the lasers to work out where the lines of trees are so that we can just drive straight down the middle. So this autonomy here is not using any GPS technology. And that's really important for many orchards because despite advances in newer satellite systems and so on for GPS, as a rule of thumb, the more sky you can see, the better the GPS will work. And you can't really get around that. It's the physical properties of how those signals come down from the satellites. And so in a lot of orchard environments where you've got canopies up over the robot, forget GPS. So this kind of technology kind of gets around that by using sensors on board to steer the vehicle appropriately. So we can still do autonomy in that way.
What are they steering off?
So that's using laser.
Yeah, but off what? At the end of every row?
No, so it's as it's going down the row, it's seeing the line of trees and
So
working
it's
out.
steering off the canopy.
So it's steering down the centre line of the canopy as defined by the adjacent trees on either side of the robot.
So the butts of the trees, is it?
I beg your pardon?
The butt of the tree it's measuring.
In this case, that particular example was just looking at generally the foliage because that one was in a kind of trellis type environment, so that's actually easier, but the same thing works in sort of discrete tree type setups where you can find the trunks and use that to define the line basically. And there are many other shapes and forms that you can do to achieve that kind of thing. So here it is, here's an example showing, this is with real data. As it drives along, it's using this laser sensor out the side and building up a kind of three-dimensional picture of the, in this case it's an almond orchard, and this is with a sort of discrete tree kind of configuration like that, not a trellis. So you can see this is sort of shown from above. You get all this nice 3D imagery of all the trees. Now we can run that data into our algorithms and software and so on, which automatically work out where one tree starts and the next tree stops. That sounds kind of obvious. It's really easy for a human to see that in the field, but to do that in an autonomous system can be challenging. So there's some interesting maths that goes into making that work reliably. So then once you've got that, you know where all the different trees are, and you can pull out three-dimensional information about individual trees. So this is just an example, a fairly low-resolution 3D laser scan of a tree. And you can start to measure things like canopy volume, rate of growth if you make measurements at different times of the year, the tree structure, and all sorts of things like this. And of course, the detail with the individual tree, but you can do it for every single tree with a system like this. Why would you care? This figure here shows basically each individual dot on this is representing one tree, and it's just showing the canopy volume from 1 year to the next year. So in this case, it's showing the nonpareil trees are growing. I think 7 or 8 year old trees in this case, so you expect them to. And if you look at the relationship between these canopy volumes and the actual yield, they're a strong driver, of course, of how much, in this case, how many nuts you get off each individual tree. Again, it's kind of obvious, right? A big tree, you get more produce from it. But actually being able to measure that on a tree-by-tree basis in a reliable, quantitative way across your whole farm can be of potential use in terms of how you manage rates of application of things like fertiliser, irrigation, whatever it might be. So here's an example of the same sort of thing just shown on the scale of, I think, about 580 trees here. We make 2 passes of the trees to see it from both sides, which is why they're coloured that way. So now we know where all the individual trees are. We can also pull out images that are taken as we drive past. We can get the images centred on each tree like this. So think of it kind of like Google Street View for the orchard, right? So you get this database of pictures. And by scanning at different times of year, you can build up a kind of seasonal and historical kind of database of what all the trees look like. So for example, we scan at the peak blossom, we scan at fruit set, and then we scan just before harvest. So for any tree, you can say, well, okay, what did it look like in this year, this season, and so on. And so you can kind of, pick out different trees and compare them like that. My mother is retired now, and she likes to travel, and it doesn't matter where she goes or for how long she goes. She comes back with 600 or 700 photos from that trip. And so I could probably get her back by showing her a database like this. So I know that you're not going to want to sit through and look at all these photos, right? So fortunately, we can write software to do it for you and extract the relevant information out of these photos that's of some sort of agronomic kind of interest. And so, for example, here, a photo of an almond tree during flower and then with the fruit, and we can automatically pull out, using machine vision software, we can pull out the sort of density of the flowers and the density of the actual fruit on the tree. And you've done that for every tree, so we can sort of build up these kind of maps. So, for example, this is a map of the flower density on this particular almond farm. Perhaps you have to squint a bit to see, but I mean, you've got this kind of alternating density pattern. That's because they use alternating different varieties for the pollination and so on. Otherwise, it's fairly uniform. If you look at that again, in just the same sort of data, look at it in a different way. So each point here is the flower density of a particular tree from one day to the next day. You can see the rate of change. So some of the varieties are increasing. They're not yet in the peak bloom, and others were in the peak bloom in the past and are now declining. And so this graph actually here shows exactly what you want to see, which is that the harvest species, like the main species, which is nonpareil in this case, the two varieties they've chosen, in order to have in bloom for pollination around the same time. Generally, they choose one, either side, and so you can actually start to quantify that is in fact occurring, for the trees by and large. Here you see the different sort of the performance, I guess, of that synchronization between the pollinators and so on. And of course, producing yield maps by combining this information together. For example, here, so red is less yield and yellow is higher yield. And you can see there's definitely an interesting pattern on the left-hand side of the figure there, where there's a whole sort of region that's not quite doing as well. In this case, the farm manager was well aware that that area next to the main access road on the property was producing lower yield, but with these methods for quantification, you can actually say more or less exactly how many trees are being affected and how much yield you're actually missing out on there. If you couple that with actual systems to do variable application of things like fertilizer and irrigation and things like that in the future, then you can start to maybe address this, on a tree by tree level and bring all the trees up to a kind of uniform performance. It's applicable to other fruits, of course. Here's an example on some mango data where the algorithm is, pulling out the different fruits and so on. Lychees, for example. And again, it's that attention to detail, right? There's hundreds of lychees there, but you can, relatively quickly sort of pull out that kind of picture with the software and do that for you. Here's an example with apples. In this case, it's a trellis, a two-dimensional trellis of apples. So as we're driving along, we're pulling out, detecting all the different apples and so on, and quantifying that as a way to estimate the yield in this orchard. And so what you see here, for example, is normally the grower will do a post-harvest weight of the produce and a count in the packing shed, and so he or she will have an idea of the yield that was on a whole block, basically. But here we did a study with that grower where we looked at estimating it on a row-by-row basis instead, so just a higher resolution. So very kindly, he agreed to weigh the produce per row, which is not normal. And that came at a cost in terms of the logistics, keeping all the buckets separate and so on. It was essentially expensive for him, and he said he'd never do it again, but he was glad that he did, and we could show that we were able to produce a similar kind of performance in terms of using the image-based systems. And one thing here is that he hadn't been aware of the extent to which there was this kind of trend in decreasing yield row by row across that particular block. And if you look at that, you can start to quantify the value that some of this information might actually have. If it's possible to address the problem that's causing those other rows to be, depressed in terms of yield, that triangle is kind of like the missing yield, and therefore a potential estimate on the dollars additional you will make if you can actually bring those other rows back up to the sort of better performance. And in this case, that grower made a change to where his pollinators were placed, because that was his belief as to what was causing that issue in that case. So I've been talking about information gathering and so on. I'm from a robotics group. Obviously, autonomous harvesting comes up. And whenever we're talking to growers, around the country, it's always number one on their list of priorities, particularly in terms of labour saving and the sort of uncertainty in the labour situation there. So I wanted to just say a couple of things about that and where we are as a community in terms of autonomous harvesting. We've had a lot of success in the broadacre, big machines like this doing, there's a person in that, but it's very readily automatable. In the tree crops, we haven't seen, nearly so much of that kind of technology coming into play. And one of the key reasons for that is essentially the difficulty in terms of, on this environment, you can see it's a much more homogeneous kind of environment. It's much more able to be mechanised, whereas in this environment, many different orchards have a very different kind of structure. There's a lot of variability in how orchards are structured, and even in any given orchard, you've got a very complex kind of three-dimensional shape there with a tree and the fruit that's often hidden and this kind of thing. So it's a much harder problem to look at. So we have this map of where all these apples are, right? So why can't we just get a robot arm and start to harvest? And there are a lot of groups around the world that have actually been looking at this for even decades. It's quite a challenging problem, and it's not going to be solved tomorrow, but progress is being made. Knowing where some of these apples are and being able to point a robotic arm, for example, to it is really only half the problem. With all the fruit being so delicate, there's a lot of difficulty in making a machine able to be dexterous enough, like a human hand, to pick that. And that tends to be one of the big sort of stumbling blocks. Though additionally, you also have problems even seeing some of the fruit hidden behind the leaves and that sort of thing. So we're still a way off getting something like this kind of technology to be sort of fast enough and cheap enough to be effective. But again, it's an ongoing sort of research problem. Just to mention this same sort of thing in another way, if you do a Google image search for fruit harvest machines, that's what you see. There's obviously a lot of work going on in mechanisation and automation in terms of fruit harvest systems. But look at the variety of all these different things. So there's as much variety going on in terms of the mechanical systems as there is in the actual orchards themselves, which you might expect. And some of these things look like they're made from parts out of a car wash. I can't imagine, that one there would do anything nice to an apple, right? So maybe, for some cases for canning or juicing or something like that, they're more appropriate, but for the fresh fruit market, it's still a little way off, I think. So just to stress that difficulty with the variability. So thinking, further forward then, you've got this problem where if you have a lot of variability amongst orchards, for example, it's going to be very expensive to build one kind of robotic or mechanised system that can really deal with that variation. Whereas if you have more simplicity and more regularity in the structure of the environment where these systems are meant to work, it's going to directly lead to lower cost in the end systems and much more capability for autonomous action. And so it raises a kind of interesting question, which is then how to structure an orchard. A lot of people look into structuring orchards, obviously, for optimal yield and optimal quality of the fruit. There's a lot of work that's been done in that and a lot of success in that area. Maybe we need to add to that to also consider the future of how autonomous systems and mechanised systems are going to come into play there, and think, can we actually meet in the middle and design orchards and these systems all together to be jointly kind of optimal in that sense. So that's sort of an interesting avenue for future research there.